Hey guys, for this video we're going to be looking at Newton's laws of motion, in particular the first two, and we're going to look at an example at the end to tie up what we've learnt. Alright, so let's look at the first law of motion. Now this is called the law of inertia, and Newton said if an object does not interact with other objects, it is possible to identify a reference frame in which the object has zero acceleration. Now, what that means, the translation, when viewed from an inertial reference frame, the velocity of an object will not change unless it is acted upon by an external force. So effectively, forces create a change in velocity. Forces create acceleration. And basically what Newton was saying is a body will continue to move with constant motion or constant velocity until a force acts upon the body. Now, it says here an inertial reference frame just because if we look at it from a non-inertial reference frame, if we look at a body from a non-inertial reference frame or a reference frame that's accelerating, it will appear like the body is accelerating even when forces aren't acting upon it. So that using the words inertial reference frame just clears that up. Just quickly, what does inertia mean? Quite a difficult concept to get your head around, but what it means is the property of an object to resist any attempt to change its velocity, right? So inertia of an object is actually what keeps the body moving at constant velocity, or keeps it at rest until a force acts upon it. So that is what the inertia of an object is. And that is essentially Newton's first law. Newton's second law says the following. When viewed from an inertial reference frame, the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Now, what does that mean? Let's have a look at the translation. What this actually means is that the net force acting on a body, so that means the sum of all the forces, or the net force, it's equal to, the magnitude is equal to the mass of the body times its acceleration, and the direction is the same as the direction of the acceleration. Now, if we look at this as a vector diagram, if we have all of these force vectors happening to a body, the net force, we know by adding the vectors tip to tail, is actually this force vector right here. So that is the force acting upon the body, the net force. Now, the net force, the magnitude of this force is equal to the mass of the body times the acceleration, one more time, and the direction, so this direction is actually the direction that the body is accelerating in. So that's all that means. And this equation is used a great deal in this course, and so it's very important to understand. Alright, just before we look at the example, we're going to look at the units of force. Now, the units of force were named after Newton, they're newtons, and what a newton is a kilogram meter per second squared. What that means is if I have 1 newton of force acting on a body, that 1 newton will move 1 kilogram, it will accelerate 1 kilogram, 1 meter per second every second. So that is essentially what newtons mean. 1 newton will accelerate 1 kilogram, 1 meter per second every second. So the velocity of that 1 kilogram will increase by 1 meter per second every second. Right, now let's look at an example where we can use Newton's laws to discover solutions to problems. Alright, so I've got an example here. Engineers at the Johnson Space Center must determine the net force needed for a rocket to achieve an acceleration of 70 meters per second. If the mass of the rocket is 45 tons, how much force must the thrust of the rocket develop? Right, so how we usually answer these questions is we do something called a free body diagram. What a free body diagram is, you model the body as a dot and you draw the forces acting on it, acting out of it. So we've got the thrust of the rocket pushing the rocket up, and we've got gravity, the other force, pulling the rocket down. That's usually how we notate gravity. Right, now the net force, as these are occurring in opposite directions, you simply subtract the force of gravity off the thrust, and we end up with this net force on the rocket, which is a little bit smaller than the thrust. Right, so that's our free body diagram. Now let's represent this algebraically. So we know pretty well now what it looks like in terms of forces. Algebraically, first of all, we know that the net force acting on this rocket is equal to mass times acceleration, as per Newton's second law. We also know from our free body diagram that the net force acting on the body is actually equal to the thrust minus the force of gravity. Right, the force of gravity has to be negative because it's occurring in an opposite direction to the thrust. So now we can equate these two things and we end up with the mass of the rocket times its acceleration is equal to the thrust minus the force of gravity. Right? Let's just rearrange because we want to find the force, the magnitude of the force of the thrust. Right, so we'll add the force of gravity onto both sides. Now, we know that the force of gravity, is equal to ma as well. But what's a in the case of gravity? It's just g, or 9.8. So the force of gravity is actually equal to mg, which is something to remember because that comes up quite a lot in Newton problems. So we can sub that in. We can see we're going to have a common factor of m. So we'll take that out. Now the mass of the rocket is 45 tons, but newtons are generally in kilograms. So let's change that to kilograms. Right, so we've got 45,000 times the acceleration of the rocket. We need 70 meters per second, if you remember from the question. And 45,000 times the gravity. So that'll just be 9.8 meters per second squared. So now we have numbers that we can just put in our calculator, and we end up with the thrust of the rocket being 3591000 newtons. 3,591,000 newtons of force is needed to push the rocket up with the desired acceleration. Now, to write this a bit simpler, you can actually write 3591 kilonewtons, just the same way as you'd write kilometers instead of meters. And that is how we answer a Newton question using a free body diagram and then representing it algebraically. And that actually concludes this lesson. Thanks, guys.
Cut study time with concise video summaries by top students. Visit spoonfeedme.com to view more free videos in this course and hundreds of others.